Okay. Our talk today will be given by Ilya Chevyrev from the University of Edinburgh, who will tell us about the invariant measure of the 2D Yang-Mills Langevin diamond. Thanks, Ilya.
Okay, thanks very much. And thanks also very much for the invitation. It's very nice to speak here in the seminar. I followed some of the talks in the past, and I've always enjoyed the ones that I've seen. So it's nice to speak here now. Um, so I want to present a work that's sort of in between constructive quantum field theory and stochastic partial differential equations. So in particular, I'm going to focus on special types of models called Yang-Mills models. And in my talk, I'm going to try to introduce them from at least two different perspectives, and discuss some recent results that we've managed to obtain in the theory with ideas from stochastic PDEs. So this is mostly based on a recent joint work from early this year with Hao Shen. And I'll also mention some earlier works that were kind of like precursors to this work with A.J. Chandra, Martin Heire, and also Hao Shen. Okay, so just to set the scene, the kind of objects that I'm going to talk about at the beginning very general stuff, so I'm not going to give that many details. And maybe some details will come a little bit later. So if you're interested in the details, just bear with me. So the kind of objects that I'm going to be interested in studying are Euclidean quantum field theories. So these can be seen as Gibbs probability measures on the space of distributions. So E here is just some finite dimensional vector space. And these measures are given by a formal Lebesgue measure on the space of distributions, weighted by this Gibbs factor, e to the minus of a certain action. And this action is typically given by something as an integral over Rd of a suitable Lagrangian density. This Lagrangian density involves the field and its potentially its derivative. So this is an extremely formal expression. As written, it doesn't make sense for almost any action any interesting action that one can take. However, there's a lot of interest in trying to make rigorous sense of this probability measure, as well as study its properties. So one of the obvious interests of this is should be somehow a very interesting probability measure. So kind of from a purely probabilistic perspective, it's perhaps worth studying. And on top of this, there's interest from at least three other fields in mathematics. So the first one is constructive quantum field theory. So in constructive QFT, the idea is that you want to make a mathematical model for elementary particles. So we're now very good at kind of smashing together particles in colliders and sort of seeing pictures of scattering particles like here. And then the idea of constructive QFT is to make a mathematical foundation for these things. So Euclidean QFTs arise from relativistic QFTs through something which is called imaginary time, or Wick rotation. So by studying the Euclidean counterpart, you can say something about the relativistic QFT. So another area where they appear is in statistical mechanics. So they frequently Euclidean QFTs arise as scaling limits of certain models, say on the lattice. So famous examples include Ising models as well as Bose-Einstein condensates. And the final field is in PDEs. So very frequently, these Euclidean QFTs arise as invariant measures for certain equations. So, for example, if you look at a Hamiltonian flow for suitable Euclidean QFTs, you get interesting nonlinear equations like the nonlinear wave or the nonlinear Schrödinger equations. And then by analyzing these Euclidean QFTs, you can say something about the equations, for example, in regimes below the kind of optimal deterministic regularity threshold. So, so as I mentioned, so hopefully I've given some motivation for studying these probabilistic objects. And so as I mentioned before, and as you can guess from the title of my talk, I'll be studying a special class of them called Yang-Mills theories. So I'm going to give a hopefully gentle introduction to Yang-Mills theories. So the very first example of this, of what a Yang-Mills theory is Maxwell's theory for electromagnetism. So let's consider fields E and B. And these are fields defined on R4, and they take values in R3. So E is going to be the electric field, and B is the magnetic field. And a very simple particular case of Maxwell's equations in the vacuum takes on the following form. And solutions to this are well known. They're characterized by these sinusoidal waves that are perpendicular to each other. And so the particular form of these equations for our purposes is not going to be so important, but there's something kind of peculiar that I just want to point out about them, which is that they involve 6 real variables, but they have 8 equations. So each of these 2 equations in the first column is one equation for scalars, and these final 2 are further 3 because this time derivative is a 3 vector. So okay, it's a bit mysterious when you see them at first, actually, where these numbers come from. So perhaps we can kind of find a different way of interpreting these equations. So the idea behind so the idea is kind of point us in the direction of general Yang-Mills theory is to consider a one form now, which is now from R4 into R4. So because the dimension is the same, you can interpret this as a one form, and this is called also a gauge field. So then we define its curvature according to this expression. This is a 2 form because it's anti-symmetric in the variables I and j. And then from this definition, so taking any one form like this and defining its curvature, we can then define fields E and B, which are going to be the same electric and magnetic fields from before, according to this equality, so according to this matrix. Okay, so far we've just made definitions. So now we can actually maybe observe something. So because of this definition, so because f is the curvature over one form, if we take its exterior derivative, it automatically vanishes. This is a special case of something called the Bianchi identity. So, or just the fact that the exterior derivative squared is 0. And if we go back to the definitions of, so if we go back to the Maxwell's equations on the previous slide, we see that for these fields E and B, this is equivalent to this expression, which is automatically verified, is equivalent to the first 2 of Maxwell's equations. Okay, so we kind of have a different way of now looking at the first 2 Maxwell's equations, which is, so perhaps we're on a promising route in some sense. Okay, so what about the second 2 Maxwell's equations? So they're equivalent to a very similar looking equation, but where we replace d by d star. D star is the adjoint of d. And this turns out to hold if and only if a is the stationary point of the so-called Yang-Mills action. So this expression is no longer automatically verified. It's only verified for certain special a, and they're exactly the stationary points of this action. So this is the L2 norm of the L2 norm squared of the curvature 2 form. Okay, so we have this new way of kind of like interpreting Maxwell's equations, which is somehow perhaps a little bit more canonical. But there's a price that we have to actually pay. So if we think about these electric and magnetic fields, which are the physical observables that we see in real life, they end up not determining this gauge field A uniquely. So in particular, if we take any function f from R4 into R, and we add to A the derivative of f, then its curvature doesn't change. So this is again the fact that d squared is just equal to 0. So really A and this A plus d of A, they give rise to the same electric and magnetic fields. So for all extent and purposes, these guys A and A plus df should be physically equivalent. So we call this A plus df a gauge transformation of the original guy A. And in kind of a very important concept in this business is that it's really only the gauge orbit of A, which we denote here by this square bracket. So the equivalence class under taking all possible gradients. This is the physical kind of the physically important object. So it's really only this gauge orbit that we care about. So we've reset Maxwell's equations by giving a new dynamical variable, which is this one form, but we had to pay a price in the sense that it's really this one form up to some sort of an equivalence class that we care about. Okay, so now we're ready to look at the Yang-Mills theory in full generality. So to set the important ingredients to speak about the Yang-Mills probability measure, which I'm going to be interested in, is a compact connected Lie group, G, which is a subgroup of UN. And the connectedness here is not terribly important, but the compactness is very important. And we're going to denote its Lie algebra by little g. Okay, so as I mentioned before, the new dynamic variables are these one forms. Now with general Yang-Mills theory, these are going to be Lie algebra valued one forms. So these are functions from Rd into g to the power d. And the important action that governs governs the behavior of these variables is again called the Yang-Mills action, and it takes on a form that's very similar to what we saw before. So it's the L2 norm of the curvature of f squared. And this can also be written explicitly in terms of the trace of these matrices. There's a very explicit form for this integral. But now the curvature is but also has this quadratic part in A. Okay, so it's important. It'll be very important that this curvature is no longer linear in A. The very first example is something that we've already seen. If we take g is equal to u1, then we recover the setting that we just saw. So this quadratic part will vanish because then the Lie algebra just becomes R. It's abelian, and we're in the same setting that for Maxwell's theory. Okay, so our aim is going to be to define and study the Euclidean quantum field theory associated to this action, which is going to be called the Yang-Mills probability measure. And I just rewrite what it should look like. So it should be some sort of a formal weighting of a weighting by the Yang-Mills action of a formal Lebesgue measure in the space of one forms. And the physical motivation behind looking at this is that, at least on R4, if we pick G to be equal to SU3, then this model, if you're able to construct it and analyze it, it should somehow correspond to the component of the standard model that's responsible for the strong force. So what's known as quantum chromodynamics. So this is a non-Abelian generalization of Maxwell's theory. Okay. So there's defining this Yang-Mills measure is quite a formidable task. It's a kind of especially in R4, it's a very famous open problem. So there are kind of two first difficulties that one notices. So the first one is that there's obviously no Lebesgue measure in the space of one forms, and especially we want it to be on distributional one form. So there's clearly no Lebesgue measure in this infinite dimensional space. And the second one is the fact that the curvature is no longer linear. So because we square the curvature in the action, we get cubic and quartic terms. So this makes it very difficult to deal with this Gibbs measure because you can't really interpret it as, for example, as a Gaussian measure anymore, like you could in the Abelian case. And these two difficulties, I call them generic difficulties here, because you witness them in other Euclidean field theories, like in scalar 5-4 theories, for those that have seen those. And then, so these are generic difficulties that one encounters essentially in all interacting quantum field theories. And then gauge theories, of which Yang-Mills is an example of, have an extra complication on top of this. So this complication is the presence of an infinite dimensional symmetry group, and we've seen this already before in Maxwell's theory when we could add gradients to a one form and not change its physical meaning. So the generalization of this here is that we call A and B, which are Lie algebra valued one forms, we call them gauge equivalent, and we write A sim B, if there exists a Lie group valued function on Rd. Such that B and A are related through this expression. So this is the correct generalization of this notion of adding a gradient of a function. So you conjugate A and you add the derivative of G. Okay, and so generalizing, so this postulate in this physical postulate in gauge theory is that A and B should be, if they're gauge equivalent, then they should be physically identical to each other. So in particular, their Yang-Mills action is the same. And so this kind of Yang-Mills probability measure, if you were to build it, it should assign equal weights to these two connections A and B. But then there's this infinite dimensional manifold now of of one forms that are equivalent to A, just because the group of all gauge transformations, these functions from RD into G, is of course infinite dimensional. So this gives a lot of problems when you're trying to make rigorous sense of this probability measure. And so at the end of the day, what you really want to do is you want to quotient out by this gauge equivalence, and you want to build a probability measure on this now nonlinear quotient space. So omega divided by this equivalence relation, where omega is somehow the space of distributional one forms. Okay, so these are the kind of the difficulties in defining this measure. So there's been quite a lot of contributions. I'm just going to review some of them to making contributions to making a rigorous sense of this Yang-Mills measure. So in 2 dimensions, this is where the most success has been. There turns out to be quite a very nice bit of a miracle, and these models end up being exactly solvable. So they kind of belong more to the realm of integral probability, if you like, rather than kind of analysis. And so what you can do is you can define a description of these probability measures via gauge invariant observables. So you can just write down the finite dimensional distribution of these measures for a sufficiently rich class of observables. And this was first noticed in the physics literature by Migdal, and then taken later up by mathematicians. For example, these are the authors I list here, but I'm missing many. Okay, then in the Abelian case, when g is equal to u1, it turns out that the curvature is now linear in A, so it has you can be made sense of as a Gaussian measure. And then the non-trivial thing that one can do is to show convergence of lattice approximations here. So this was done by Gross and Driver in the 80s. And in 3 and 4D, which is the most, in the non-Abelian setting, which is the most challenging task, there's been very little progress, and the kind of the state of the art is if you work on finite volume on the torus, you can get a kind of quite a weak form of ultraviolet stability, so kind of a weak form of compactness. And recently, there's been quite a lot of renewed interest in this model, especially from the side of probability theory. So there's been a lot of recent results that analyze these Yang-Mills measures on the lattice, which I will actually present the Yang-Mills model on the lattice a little bit later, and in the continuum. So again, I give a non-exhaustive list of people contributed here. Okay, so I mentioned before the focus of my talk was Yang-Mills theory. So if you like, the sub-focus of my talk will be to say something about this Yang-Mills theory using stochastic quantization, which I'll describe in the next slide. And I'm going to focus primarily on the 2-dimensional case. I'll say only a little bit about 3 dimensions. And it's worth pointing out, actually, even at this stage, that Yang-Mills theory was actually the original motivation of introducing stochastic quantization by Parisi and Wu. So they kind of saw stochastic quantization as a particularly nice way to study Yang-Mills theories. Okay, so what is stochastic quantization? So the idea behind stochastic quantization is that given any probability measure of this type, say it's a Gibbs measure, you want to study properties of this measure using the associated Langevin dynamic. So, so the Langevin dynamic is the formal gradient descent along this action. This is somehow some sort of a PDE now. I'll give an example of this again a little bit later. And Xi here is a space-time white noise. So the motivation behind trying to use this kind of the green guy, the Langevin dynamic, to study the blue guy, the measure, is that the measure should be invariant for this Langevin dynamic. This should be a Markov process with invariant measure mu. And then under good assumptions, or under rather good conditions, it should hold that the limit as you send kind of, so what you're doing is you're introducing an auxiliary time dimension, and you're letting from any initial configuration, you're following the gradient descent, plus you're adding random jumps and random forces in different directions. You kind of like introduce a heat path. So the idea is that no matter what one form you start with, or configuration that you start with, if you let time evolve for long enough, this will be a random variable, and in law it should converge to its invariant measure, which is this this Euclidean QFT. So that's the basic idea. And this is completely analogous to Markov chain Monte Carlo. So in practice, a lot of people actually use this to sample from a probability distribution that you know very little about. But if you can find a Markov chain or Markov process that has this probability distribution as its invariant measure, then this gives you a way to sample from it, at least approximately. And then, of course, it's also actually interesting to focusing on studying the measure using the Langevin dynamic, but you can go the other way as well. You can study the dynamic using the measure. So this is also of interest. So, so this is I want to present like a bit of a schematic picture of recent success in this program. So there's been a lot of success in using stochastic quantization for a simple 5-4. Well, it's still complicated, but it's one of the simplest Euclidean field theories you might think of in 3 dimensions. So here the kind of corresponding Lagrangian densities of this form. So it has this square of a gradient term, and it has this quartic interaction. This is why it's called 5-4. And then the corresponding stochastic PDE is of this type. So this is a singular stochastic PDE for which it's non-trivial actually to make to kind of give solutions to. And the idea is that this C, which we'll see a little bit later off here as well, is some sort of renormalization constant that one adds to the equation to make it well posed. So then, so in this picture, you can sort of see that there's 2 arrows going from the 2 sides. So you can kind of use ideas from Euclidean quantum field theory to study the SPD. So for example, you can use it to give long time existence for this SPD, and you can also use ideas from QFT to give actually novel solution theories for these SPDs. So for example, based on renormalization group. And then there's an arrow going from the kind of SPDs to Euclidean QFT. So you can use the actual dynamic to give a new construction of the measure. So if you show that this invariant measure, if you show that the Markov process has an invariant measure, this gives a construction of the measure. And you can also use the PD to prove so-called Osterwalder-Schreiber axioms, which are very important for effectively developing a physical theory from this probability measure. Okay, so the underlying question that we were asking when we started on this work is that whether a similar picture can be obtained for Yang-Mills in either 2 or 3D. So the basic questions that one might ask about Yang-Mills is, so can you actually solve the Langevin dynamic in 2 dimensions in some sort of a meaningful way? If you can do that, is the 2-dimensional Yang-Mills measure, the simplest one that I mentioned that has this exact solvability property and is well known, will it be invariant for this Langevin dynamic? And also, can we use the dynamic to learn properties about the measure? So I'm going to speak primarily about the second 2 questions, and I'll mention this first one on the next slide. So this first one, so all of them end up having an answer, a pleasing answer, yes. So the first one we answered together with A.J. Chandra, Martin Heyer, and Hao Shen. This is published last year, but it actually appeared in the archive in 2020. And then we have a joint work with Hao Shen early this year that focused on the final 2 questions. Okay, so the first result that I actually want to present to you is this one that we obtained with A.J. Martin and Hao. And it answers that first question, whether we can solve the Langevin dynamic in some meaningful way in the case of 2 dimensions. And also, as I didn't specify this, but we're always going to focus on the torus. So we're not going to worry about what happens in the so-called infrared limit, so in Euclidean space. So we're always in a box. Okay, so the statement of the theorem is let psi be a G2 valued white noise, and to consider a mollifier chi, which is non-anticipative. So basically, the mollification of psi with the mollifier should be adapted to the filtration generated by psi. Then the statement of the theorem is that there exists this is a linear map from G into G. such that solutions to the stochastic quantization equation for Yang-Mills that I write it down here with two added terms. There's a purple term here added and an orange term added. So if you ignore this purple and orange term, this would be exactly the equation that, the generic kind of stochastic quantization equation I presented a couple of slides ago, modulo this modifier. So if you look at solutions to this, so these are smooth solutions because the noise is now smoothened out. At least these are smooth local and time solutions. Just before I conclude the statement, notice I give also on the second slide the kind of the way in which the equation looks like. So this is a heat equation. So the leading order is a heat equation, and it has this cubic and quadratic part. So the quadratic part is a times the derivative of a. So this is, of course, all of these actual nonlinearities are Lie brackets, because that's the only thing that you can kind of use in the Lie algebra. But you have these kind of, the nonlinearities are of this form. Right, so if you look at solutions to this to this PDE, started from some sufficiently nice initial condition A, then they converge to a Markov process that has values in a suitable Banach space of distributional one forms. So think of this, maybe this Banach space as just being some suitable Hol-de-Besov space of distributional one forms. Okay, and this first statement holds true actually for any choice of this orange guy C. So so there's nothing special about this choice of C here. But if the special choice of C comes from the second point, which is that this, if you look at now this this one form evolving in time, and you project it to the quotient space, so you quotient out by gauge equivalence. So this Banach space is specifically set up so that gauge equivalence extends in a canonical way to it. Then if you quotient out by gauge equivalence and you project the Markov process from the first guy down to the quotient space, then this new guy remains a Markov process. And this is a highly non-generic property because if you take a Markov process on any space and you project it down to a subspace, there's no reason that projection will be Markovian. But in this case, if you choose the value of C correctly, then this you obtain this property. Okay, so okay, let me not worry about the first 2 points. Maybe just let me make a remark that we obtained actually a similar result last year in the three-dimensional setting. The main difference is that you actually need to insert a divergent counter term into here, so into the SPD to make it converge. And this the space omega, it has to be it ends up being a nonlinear space. So you kind of work with Banach spaces. Moreover, inside of the statement that we proved in this work, there's no claim about the uniqueness of this constant C, but actually ends up being unique. So this is something that that we proved later with Hao. So I'll speak about this if there's time a little bit later. Okay, so just before continuing, this is roughly the schematic picture of what is happening. So if you start this this Markov process upstairs, so this green and the red guy, that they're actual solutions to the parabolic singular stochastic PDE from two gauge equivalent initial conditions A and B. So these black lines are supposed to be equivalence classes. Then if you run them to any positive time t, there's of course no reason these two guys are equivalent in law. I mean, you started them from two different initial conditions, so they're not going to be equal in law. But what happens if you project it down to this quotient space, and you look at the evolution of this of the quotiented guy, then these two, this kind of green, or the red trajectory and the green trajectory, they get pushed down to the same trajectory in law. So this is schematically what that theorem is saying happens. Okay, so so the kind of the result that I want to now add to this to that previous one is going to focus now on that second question that I asked. So now that we have a good Markov process on the quotient space, it's perfectly meaningful to ask whether the well-known two-dimensional Yang-Mills measure is invariant for this Markov process. So this is the content of this other work that we did, and it basically says that indeed that's the case. So this projected Markov process indeed has a unique invariant probability measure, and moreover, this probability measure coincides with the two-dimensional Yang-Mills measure. So an important remark is that the actual SPD for A, so the one that I wrote down on 2 slides ago, that might not have an invariant measure itself. So we make no claims about the invariant measure for the SPD. This is already very easy to see in the Abelian case. So in the Abelian case, it happens kind of for harmless reasons, but it already tells you that something non-trivial is going on. And you have to be a little bit careful. And on top of this, just to show how bad the situation is, we don't actually even know long-time existence for the deterministic, or I should say I don't know the long-time existence for the deterministic Yang-Mills flow. So kind of showing that, so without the deterc term, which I didn't speak about, but that was the purple term 2 slides ago, but kind of without the deterc term, there is a well-known long-time existence result, but if you make the equation parabolic as we did, then it's not known that you even have long-time existence there. So let alone for the stochastic PDE. Okay, so for the rest of the talk, I want to very briefly talk about some of the steps that go into the proof of this result. So on a kind of bird's eye view level. And then maybe mention some corollaries and give some further directions that one might be interested in looking at. So the general steps of the proof involve, so there are 3 main steps. The first one is to derive moment bounds on suitable lattice approximations of the measure. So this is nothing about the dynamic. This is just a question about the Yang-Mills measure and its approximations. The second step is to consider the Langevin dynamic associated to these lattice approximations and show that it converges to some sort of a continuum limit. And then the final step, you want to actually show that that continuum limit is the same one that was identified in the using other methods. So the one that we had in the previous work. And then so if you can prove these 3 steps, then they all combine into in a relatively standard way with something that's called Bourgain's invariant measure argument, or Bourgain's globalization argument. So I won't spell out how to combine these, but there's kind of a well-known way to do this. Okay, so let me start with this first step, which is the lattice approximation of the Yang-Mills measure. And this also will give actually a different perspective on the measure. So I previously spoke about it kind of in the continuum using a somewhat geometric flavor. I'm now going to speak about it kind of coming more from statistical mechanics. So this is actually how we analyze it in this work with Hao. So so consider so we're going to continue working on the lattice. So we're going to continue working on the torus. So consider a lattice with spacing epsilon. Which is I'm going to assume that it's some negative power of 2. So something that looks like this, and with the opposite sides identified because we're in the torus. So the important objects in this lattice are actually going to be the edges. So they're not sort of the edges play a more important role in some sense than the vertices. So I'm going to call the set of edges E, and I'm going to assume that they're all positively oriented. So these edges have an orientation, like in this diagram. So the configuration space for the discrete approximation of the Yang-Mills measure are functions from these edges into the group G. These are all functions from E into G. And we're going to, for what's called a plaquette. So a plaquette is basically a square inside of this lattice. So here there's some, I don't know, 64 of them or something. So for each one of these plaquettes, we define the discrete notion of curvature, which is here denoted by U partial P, according to this product. So this is now a group valued object. So where alpha I are given according to this diagram. So what one should think of is that u, which is belonging to an edge that goes from x to x plus epsilon ei, this should be approximately equal to e to the epsilon times the one form evaluated at x. So then if you apply Campbell-Baker-Hausdorff and you drop negligible terms that are lower powers of epsilon than epsilon to the 2, you end up with this expression. So u around this plaquette, so what's called the holonomy of u around the plaquette, this is approximately e to the epsilon squared of the curvature of this A. Okay, so this is the configuration space, and these curvatures are going to play an important role as we now see. So the lattice approximations of the Yang-Mills measure are going to be Gibbs probability measures on this configuration space. So these are going to be probability measure on the space of functions from E into G. They're going to take on a form like we saw before. So we have now a Haar measure inside of this Gibbs measure. This is the product Haar measure when you take the product of all the edges. And you weight by a discrete approximation of the Yang-Mills measure. And these discrete approximations of the Yang-Mills measures, we're going to take them of this form. So we're going to sum over all plaquettes, so all squares inside of the lattice. We're going to evaluate this discrete curvature at the plaquette at this little s. So this little s is going to be something that's going to make this guy approximate the discrete, approximate the continuum Yang-Mills energy. So locally, it should look something like, so for x close to the identity in the group, it should look something like epsilon to the minus 2. This minus 2 makes sure that everything scales correctly so that you get the L2 norm squared of the curvature in the end, and multiplied by the logarithm of this group element x, and then you take its size inside its norm inside the Lie algebra and you square that. So well-known examples of this include the Wilson action. So for the Wilson action, you you take for this s epsilon to the minus 2 times the real part of the trace of I minus x. And for there's another very useful approximation, which is called the Villain or the heat kernel action, which is where you take the heat kernel associated to the Laplace-Beltrami operator on G. You look at that heat kernel at time epsilon squared. You take its logarithm, and you evaluate that at that group element x. Then you add on a certain constant just to make sure that you have this exact expression. Otherwise you might not. This thing might be sort of too large or too small. Okay, so this is what the lattice approximation of the Yang-Mills measure look like. So an important point to remark here is that of how gauge invariance manifests here. So the ground state for this action is where the action is equal to 0. So this is obtained when u is equal to 1, but this is not unique. So just setting all the group elements to all the edge variables to 1 is an example of a ground state, but it's not a unique ground state. And in fact, if you take any function that goes from the lattice to G, you kind of apply this now discrete gauge transformation to this discrete gauge field U according to this formula, which is the kind of the analog of the gauge transformations we saw before, then again these two guys are going to be physically equivalent. So so in particular their actions are going to be the same. So just as an example here, if this was our entire lattice, so without periodic boundary conditions, if the whole lattice which just consisted of 4 points, then this configuration, which is a ground state, so a flat gauge connection it's called, is gauge equivalent to this one. So even though they look quite different, they actually they're going to be physically equivalent. So this is a bit different from many statistical mechanics models that we're used to, because here now we have this whole manifold of ground states, and this dimension of the manifold is the lattice, as the number of points in the lattice grows, it also grows. So it's going to grow to infinity. Okay, so this is a very particular feature of this lattice gauge theory. So what we're going to be, so on the next slide, I'm going to present this solution to kind of like step one of this heuristic proof. So to kind of to set things up, we're going to consider a loop inside of this inside of our lattice. So this will be an ordered collection of edges. And here we're allowed to take reverse edges, so edges can be pointing in the reverse direction. That's what this little arrow here means. So an example, this would be a loop on our lattice. And then for one of these discrete gauge fields, we define the holonomy along the loop as just the ordered product of the gauge field evaluated at E. And if we ever orient and kind of go along an edge in the reverse direction, then we impose that the definition of U at this reversed edge is U inverse, U at E inverse. And then the Wilson loop, according to this, associated to this loop, is just the trace of the holonomy. This is a complex number. So then an important lemma is that if U, and which is quite easy to show, is that if U and U tilde, U and U bar are gauge equivalent, then all of their Wilson loops agree. And it actually turns out that for many G, the converse to this statement also holds. So if they agree for all Wilson loops, then they're gauge equivalent. So if you like, it's safe almost to assume that this is an equivalence between the two of them. So this is why Wilson loops are interesting. So then the solution to this step one in the heuristic proof that I gave before. So this is establishing moment so finding good approximations for the Yang-Mills measure and establishing moment estimates for them is given here. So there are two results that are important for us. So consider this discrete Yang-Mills measure and and consider UE to be the distributed according to this thing. I don't know why I have this EG here. So this is a random variable taking values in this space, distributed according to this one of these discrete approximations of the Yang-Mills measure. So then suppose that this discrete approximation is really taken from the Villain action. So the heat kernel action I showed before. So what Lévy in 2003, and also actually I should mention in 2006, there's a follow-up work that he did. What he showed is that there actually exists a stochastic process in the continuum indexed by all lattice loops. So all loops that belong to some sufficiently fine lattice, such that as you take epsilon to 0, the Wilson loops for these discrete approximations, they converge to this continuum limit in the sense of finite dimensional distributions. Okay, so this gives this shows that this Villain, the approximation that I described before, given for the Villain action, is a good approximation for the continuum limit. So the stochastic process formally comes from this two-dimensional Yang-Mills measure. This is how people actually defined the two-dimensional Yang-Mills measure before. Okay. And then the second result that's important for us is that is the moment estimates. So this we proved in the work that I'm describing, and this followed work that I did several years ago on kind of pure lattice gauge theory. So the statement is that for sufficiently nice approximations, which include both the Villain and Wilson action, and you can quantify what nice means. There exists a random gauge transformation, so a random function from the edges. This should be from the sites lambda to G, so not E, but the sites lambda to G, such that for all P and kappa, this the expectation of the gauge transform U. When you gauge transform U according to G, and you measure its regularity in some suitable negative Holder-Behe subspace. So the pth moment of this norm is bounded uniformly in epsilon. So the reason that you want kind of these moment estimates and why you need to really gauge fix this random variable u is because kind of the SPD it likes to take initial conditions that are sufficiently nice. So if you start from initial conditions that are very, very rough, you can't really say anything about your stochastic PDE. And as we saw, there's a lot of gauge freedom in this U. So even if you take U which is flat, so in somehow the case where you're kind of at zero temperature in statistical mechanics lingo, U itself could be very, very rough, just because you can gauge transform it to be as arbitrarily rough as you like. So this is why this gauge transformation here is very important. Okay, so that completes this step one in this sketch proof. So step two, I'll just describe very briefly. So if you write down the Langevin dynamic associated to one of these discrete approximation of the Yang-Mills measure, and you take its logarithm. So you look at it as a diffusion now on the Lie algebra. So functions from the edges into the Lie algebra. It takes on a form like this. So it has the same leading terms as the Yang-Mills action as the continuum Yang-Mills Langevin dynamic, but it has a remainder that's actually ends up being very singular. So this remainder has, for example, multiplicative noise, and it's quite a singular term. So the valid result that allows us to obtain some continuum limit for these dynamics is the following so-called universality of the dynamic result. So what it states is that there exists some sort of a linear map C bar, such that for sufficiently nice U epsilon, so these sufficiently nice approximations, these solutions to these discrete PDEs, they converge to a process A in probability as epsilon goes to 0, where A solves the same continuum Langevin dynamic, except rather than having the C, which was in the statement in the kind of the that I presented from our first work, is replaced by this C bar, and the C bar is quite inexplicit. It's quite difficult to compute. Okay, and so what remains is to show us that this shows that there exists some nice continuum dynamic for these discrete SPDs. And what remains to show is that the C bar is actually equal to C, so the good constant in the continuum limit. So the trouble with this is that there's many order 1 contributions to the C bar that come from cancellations and approximate parity. So approximate parity means that you don't have exact integration by parts, which typically makes lots of constants vanish. So it's very, very difficult to give an explicit expression for the C bar. You can show it's finite and that it exists, but calculating it is very, very delicate. And moreover, the situation is quite bad because we can't really renormalize this Langevin dynamic. So if we could just add on some sort of a mass term to this discrete dynamic as we liked, we could just fix this problem and kind of hit the target continuum dynamic as we liked. But we can't do that because we started off with a very rigid kind of gauge invariant probability measure, gauge covariant rather. And so we need to preserve this invariant measure. So we really can't touch this this discrete Langevin dynamic. So instead, what we do is we prove that this constant C, the one that appeared in the previous statement, is actually unique. So once you do that, then you can justify that actually this C bar has to equal to C, just because the lattice dynamic also preserves gauge covariance. So the way that in the final couple of minutes that I have left, I want to present this final result. And this is now a result that's independent at all of this discussion on the lattice. So this is a result about the uniqueness of this constant C, the gauge covariant constant. And we're quite happy when we actually saw this, because it means that we didn't have to go through a very painful calculation of that C bar constant that we had before. So the statement of the result is that consider any C bar that's different from this good constant C that we had before, and you look at solutions to this Yang-Mills Langevin dynamic. And you started from two initial conditions. One is just 0, and the other is something gauge equivalent to 0. Then we consider a loop. So this loop happens to be a non-contractible loop around the torus. The statement is that for all t sufficiently small, you can find a good choice for this G, so a good choice for this initial condition B0 that potentially depends on the T. such that the expectation of Wilson loops associated with this loop of A evaluated at t and B evaluated at t has a lower bound, which is of order t squared. So the reason that this is a useful lower bound is that in the other situation where C bar is actually equal to C, then it's easy to kind of extract from the proof of our previous work on 2D Yang-Mills that these two expectations of these two Wilson loops actually have an upper bound which is of order t to the m for any m. So there's this kind of like big difference between this lower bound and this upper bound. And just a word on the idea of this proof is that basically we're looking at small time. So what one does is you look at a Euler expansion or Euler estimate for this SPD that we derived using ideas from regularity structures and rough path theory, and then this you need to find a good choice for this gauge transformation G that kind of ensures that you don't have any cancellations between these the expressions for these two Wilson loops. So here we appeal to some kind of ideas from sub-Riemannian geometry. Okay, so just to conclude, this was the first. So kind of what we aimed to do was give this first rigorous link between the Yang-Mills Langevin dynamic and its Euclidean Q of t. As a corollary, one can actually so kind of there's I think two nice corollaries that one could derive from this, which answers the third question that I posed in the middle of the talk. So can you use the dynamic to study the measure? So this universality of the dynamic can actually be used to prove a universality for the actual measure. So you can actually show, for example, that Wilson the lattice approximation with the Wilson action on the torus converges to the two-dimensional Yang-Mills measure before. So this was actually for the case of the torus with Wilson action, this wasn't actually known, at least as far as we're aware. And another corollary is that it gives a nice way to give a decomposition for the Yang-Mills measure into something like a GFF plus a smooth perturbation, so an almost Lipschitz perturbation. And this gives very sharp regularity results in the measure. So, so the next kind of thing that there's lots of things still to do, but I think one of the main challenges is to actually look at what happens with non-exactly solvable models. So the two interesting ones, in my opinion, are the two-dimensional Yang-Mills Higgs model. This still hasn't been this model still hasn't actually been constructed in the non-Abelian case, and the 3D Yang-Mills measure, on which I mentioned that one only has a form of ultraviolet stability. And actually, there's still actually quite a lot of open problems just for even the 2D Yang-Mills measure, which I just list some of them here. Okay, so that's actually where I want to end my talk, and I thank you very much for your attention.